Greetings everyone. I am pleased to present to you the following research paper entitled, Enhancing Multiferroic Properties of Lanthanum Ferrite by Nickel Doping. The content of this presentation is divided as follows. Introduction, background, justification, hypothesis, objective, experimental development, results and discussion, conclusions and references. As an introduction, let us ask ourselves, what is a multiferroic material? Well, a multiferroic material is one that presents more than one ferroic arrangement, either ferroelectricity, ferromagnetism, or antiferromagnetism. Among these materials, lanthanum ferrite stands out. Lanthanum ferrite is a multiferroic material of the improper type at room temperature. This material is of great interest due to its magnetic behavior, which is used in technological applications such as transformers. It also has low polarization with respect to ferroelectric materials and is easy to synthesize. Ferrite is a material that crystallizes in a type of orthorhombic structure in ambient conditions. It is a ferroelectric material that, being improper, has a G-type antiferromagnetic order resulting from superexchange interactions in the iron-oxygen-iron bonds and presents high leakage currents. Background. Over time, work has been done on the synthesis of lanthanum ferrite, first to obtain successful synthesis to be able to study its magnetoelectric properties. In 2009 it was successfully synthesized by high-energy mechanical milling. Later in 2011 it was discovered that at 800 degrees Celsius ferrite is obtained without secondary phases. Then in 2015 it was categorized as a multiferroic of improper type, which made interesting the need to modulate its properties by doping, one of them in 2019 with nickel, which proved to decrease the band gap of the material. The reviewed literature suggests that doping for modulation and control is ideal to accentuate desired properties in this orthoferrite. Although there are some studies on the material, there are no systematic studies on the multiferroic properties and their coupling as a consequence of doping by cations with different properties. Nickel is chosen because it complies with the Hume-Rothery rules as it has a difference between ionic radii of less than 10% and they have very similar characteristics as shown in the table, which gives the indication that it would be easy to substitute. The goal of this research work is to induce the magnetic order change of LaFeO3 by doping with Ni2+ metal cations at Fe3+ positions and to analyze the effect on its magnetoelectric properties. The synthesis was performed by high-energy mechanical milling using precursor oxides which were compacted and sintered at 800 degrees Celsius for further characterization. To obtain information about their crystalline structure, magnetic and electrical properties and chemical composition, the pellets were characterized by X-ray diffraction, vibrating sample magnetometry, LCR impedance spectroscopy and X-ray photoelectron spectroscopy. The characterization performed by X-ray diffraction of the pellets obtained from the compaction and annealing heat treatment at 1073, resulted in diffraction patterns that after applying the Rietveld refinement are shown in figure, from which it was possible to identify the orthorhombic lanthanum ferrite phase with space group PNMI, for the undoped sample proving that the stoichiometric calculations used were correct. In all LaFe1x and IXO3 patterns with 0.105, the main diffraction peak is seen between 37°–38 degrees, whereas the dopant concentration increases, this peak shifts towards higher values of 2 theta, indicating a decrease in the interplanar distance, i.e., there is a higher concentration of atoms in the unit cells, which is a consequence of the difference in ionic radius between Fe3+, 0.645a, and Ni2+, 0.69a. An increase in peak width is also observed, which is attributed to a loss of crystallinity in the material due to the dopant and its accommodation in the crystal structure. The LFO as mentioned above, crystallizes in a G-type AFM structure, which tells us that by the spatial arrangement of the Fe3+ spins, with intrinsic angular momentum orientation result in opposite spin orientations, so that their magnetic moments are cancel each other. Now, the magnetic behavior is a consequence of the superexchange interactions between the Fe3+ and O2 bonds, so modifications of the structure will have direct repercussions on the magnetic order of the ferrite. To observe the magnetic behavior, with vibrating sample magnetometry, magnetic hysteresis cycles were obtained from the pellets, shown in figure, where according to the mentioned crystallization, the undoped sample presents AFM behavior unlike the doped samples, which tells us that these cations induce a weak ferromagnetic order in the doped ferrite. In general, the results show that the magnetic structure modified by cantilevering produces an inverse DM interaction, obtaining a change in the magnetic order from antiferromagnetic to ferromagnetic. The figure shows the relative permittivity values as a function of frequency. It is observed that for low frequencies, below 100 Hz, there is a maximum permittivity that begins to decrease as the frequency increases for the doped samples. However, in the undoped sample is something that does not happen. This is attributed to Maxwell Wagner behavior, which tells us that large contributions, especially at low frequencies, may be due to charge accumulators that could be defects such as grain boundary vacancies or porosity, which contributes to the dielectric loss or increase in conductivity. Dielectric losses are shown, which are observed to increase in the doped samples with respect to the undoped one. The behavior can be associated to oxygen vacancies that could be generated to compensate the charge by the difference between Fe3+ and Ni2+, which can generate the presence of Fe4+ that, when forming bonds with oxygen, can polarize when subjected to an electric field. The vacancies favor the mobility of the charge carriers, increasing the electrical conductivity. Resistivity data were obtained, which indicates by its values that it is a semiconductor-type material. It can be observed that as the concentration of the dopant increases, the resistivity decreases, which is related to the increase of vacancies that favor the mixed conductivity of the material and are associated with the difference in permittivity that exists between iron and nickel. That said, an increase in conductivity is also observed with some saturation values related to random diffusion of charge carriers. The XPS characterization allowed to know the chemical composition of the samples. The general spectrum and those of the elements lanthanum, iron, and oxygen are shown. In the oxygen spectrum there are peaks characteristic of the oxygen contribution of the lattice and of the vacancies in the same lattice. In the iron spectrum there are the peaks corresponding to IRON2p that refer to the iron 3+ states, and finally the characteristic multiplets of trivalent lanthanum that corresponds to ferrite, that is to say, the chemical composition proves the presence of lanthanum ferrite. In conclusion, it was possible to synthesize lanthanum ferrite without impurities. There was a structural distortion, including a rearrangement of oxygens that had an impact on the change of magnetic order from antiferro to ferromagnetic. The induction of the FM order modified the ferroelectric properties of the material, semiconducting, ferroelectric and Maxwell Wagner behavior. The chemical composition was congruent with lanthanum ferrite and showed that there is adsorbed oxygen related to vacancy generation as a charge compensation mechanism to maintain the neutrality of the material. Some references are shown. Thank you for your attention.